Okay, thank you very much, Lukas, for the introduction, and thanks a lot to all of you guys for coming to listen to me speak today. So it's a great pleasure to be speaking today on Sophie Germain's 250th birthday. Sophie Germain is certainly one of my mathematical heroes, and she did lots of her work on subjects that are very close to my heart. So I'm going to talk about Sophie Germain and prime numbers. So I'm going to talk a bit about prime numbers and then a bit about Sophie Germain and prime numbers. Then I'm going to talk about how prime numbers and Sophie Germain come and affect us in the real world, both for me as a research mathematician, but also wider implications. So to start off, let's think about prime numbers and how they relate to Fermat's last theorem, which is maybe the most famous theorem in mathematics, and also was the key area in which Sophie Germain worked, and is her favorite theorem. So prime numbers are building blocks of whole numbers, and maybe if you want to look up a definition of a prime number, it's just a whole number which is bigger than 1 that can't be written as two smaller whole numbers. So it can't be written as a times b for two smaller whole numbers, a and b. And so, for example, 15 is not a prime number because it can be written as two smaller whole numbers multiplied together. It's 3 times 5. But 7 is a prime number. The only way to write 7 as whole numbers multiplied together is 7 times 1, and that's not two whole numbers which are both smaller than 7. So if you first see this definition, it looks like a strange mathematical curiosity that has no real importance whatsoever. You know, mathematicians maybe study strange properties of numbers. This is certainly a property of numbers, but it doesn't seem to have any real important significance. But the key point as to why prime numbers are important is because they take the role of atoms of arithmetic, or these building blocks of arithmetic. And any whole number can be broken down into prime numbers multiplied together. And it's the so-called fundamental theorem of arithmetic that this can be done in essentially a unique way. So here, 135 is 5 times 3 times 3 times 3, and apart from changing the order in which you're multiplying the 5 and the 3 3s, it always breaks down into 5 and 3 3s. And so I like to sometimes imagine whole numbers as like molecular chemicals that are all joined together, and then the atoms are the prime numbers that make up a number. And the reason that this is useful is that if you have some problem involving whole numbers that somehow involves multiplication, because prime numbers are the atoms of arithmetic, you might be able to break that big, complicated problem involving whole numbers into a simpler problem just involving prime numbers. So this is in exactly the same way that a chemist might try and understand chemical compounds, and you can get a good understanding of many of the chemical properties of a compound by understanding the constituent atoms. It doesn't tell you everything about a molecule, but it gives you lots of important information, and this is often a simpler problem. So there's this basic philosophy that sometimes when there's multiplication involved, you can reduce a difficult problem involving whole numbers to a simpler problem about prime numbers. And this is, I want to demonstrate this through an example, and the example is going to be Sophie Germain's favorite theorem, favorite problem in the whole of mathematics, which is Fermat's last theorem. So Fermat famously claimed that there are no solutions to a to the power n plus b to the power n equals c to the power n in whole numbers a, b, c, and n when n is bigger than 2, apart from the obvious ones when you set one of a, b, or c to be equal to 0, and then you have solutions like a equals c and b equals 0. So there's a few obvious solutions, and if you exclude those obvious ones, there should be no solutions at all when n is bigger than 2. When n equals 2, this is the Pythagorean equation, a squared plus b squared equals c squared, and it turns out that there's infinitely many different solutions here. So this was famously conjectured by Pierre de Fermat, and it was then solved by Andrew Wiles, one of my colleagues at Oxford, as one of the pinnacles of pure mathematics. But this is a problem involving whole numbers, And it involves a certain amount of multiplication, because we have a to the power n, which just means a multiplied by itself n times. And so because it involves multiplication, you might hope to break it down into a simpler problem involving just prime numbers. And it turns out that this is the case, and it's enough to prove Fermat's last theorem just when the exponent n is a prime number. And in fact, it's not too difficult to see this. So let me show you a proof of this. Imagine that Fermat's last theorem was actually not true, and there was a counterexample when n is 15, so a number that is not a prime number. So that means that there would be some whole numbers a, b, and c, such that a to the power 15 plus b to the power 15 would equal c to the power 15. Well, what is a to the power 15? That's a multiplied by itself 15 times, and I could group those 15 copies of a multiplied together as 5 copies of a times 5 copies of a times 5 copies of a. And then if you think what that means, each of those 5 copies of a is a to the power 5, and we have then 3 copies of that multiplied together. And so algebraically, this is saying that a to the power 15 is a to the power 5 to the power 3. And so this is something that sometimes maybe you've learned in school about rules of exponentiation. And since a to the power 15 plus b to the power 15 is equal to c to the power 15, and a to the power 15 is a to the 5 to the 3, that means that we have that a to the power 5 to the power 3 is plus b to the power 5 to the power 3 is equal to c to the power 5 to the power 3. But now we have 3 numbers which, when they get cubed, we have the first one plus the second one is equal to the third one. And so this is a counterexample to Fermat's last theorem, where the exponent is now not 15, but is equal to 3. So if there was a counterexample when the exponent is 15, we would get another counterexample when the exponent is 3, just by using the same numbers. And if you follow through what this proof really means when I replace 15 by a different number, if there was a counterexample to Fermat's last theorem with some exponent n, then we get a counterexample when the exponent is any prime factor of n. And that means that if you know that there's no counterexamples for any prime exponent n, then it's impossible for there to be any counterexamples for any non-prime exponent n, because if there was a counterexample for a non-prime exponent n, it would give a counterexample for a prime exponent n. So that means that it's enough to just prove Fermat's last theorem with n being prime. Now, if there's maybe a couple of you at the back who are not totally convinced by this, because this argument slightly breaks down if I was thinking of n as being a power of 2, like 8 or something like that, I would just reduce it down using this argument to there being counterexamples to Fermat's last theorem with n equals 2, but we know there are examples to the Pythagorean equation. But Fermat himself knew that there were no solutions to Fermat's last theorem when n equals 4, and so this means it really is the case that you just need to consider Fermat's last theorem with n being a prime, and in fact you can just consider an odd prime. And so we've taken this equation, the most famous equation in the whole of mathematics, that involves whole numbers being multiplied together, and we've reduced it down to just proving it when the exponent is a prime number. And so this is hopefully a simpler problem about prime numbers that makes it easier for mathematicians to solve. And it turns out there are various technical ways in which this is a simpler problem, and this is essentially the first step in Andrew Wiles's proof of Fermat's last theorem. There wasn't quite enough space in the slide for me to complete the full proof. Let me give a bit of a justification as to why Fermat's last theorem with a prime value of n is an easier question than Fermat's last theorem with a non-prime value of n. So I've claimed that we've reduced down to a simpler problem about primes, but I think this is not obvious at all. And this follows from some of the nice patterns that you have with prime numbers. So prime numbers have all these fascinating properties, and often I remember I liked to just play around with numbers and prime numbers when I was younger. So we can just think about looking for patterns, and the pattern that I want to look at is what remainder is left when you raise numbers to powers. So let's start about thinking about raising numbers to the power 3 and think about how much bigger they are than multiples of 3. So 1 to the power 3 is 1, which is 1 more than a multiple of 3. Okay, that's a bit of an uninteresting statement on its own. 2 to the power 3 is 8, and 8 is 6 plus 2, so that's 2 more than a multiple of 3. 3 to the power 3 is 27, and, well, 27 is a multiple of 3, but I'm going to write it in a slightly funny way of being 3 more than a multiple of 3. And maybe you're starting to spot a pattern. 4 to the power 3 is 64, which is 4 more than a multiple of 3. And 5 to the power 3 is 125, which is 5 more than a multiple of 3. Okay, so hopefully you've seen a pattern here, and it turns out that if you take any whole number x and you cube it, x to the power 3 is x more than a multiple of 3. So this is not totally special to 3, so let's see what happens with 4. So 1 to the power 4 is 1 more than a multiple of 4. That looks good. But 2 to the power 4 is 16, which is not 2 more than a multiple of 4. It's a multiple of 4 itself. And so the pattern that we seem to see is broken down with 4. And it gets worse. 3 to the power 4 is 81, which is 1 more than a multiple of 4. It's not 3 more than a multiple of 4. But 4 to the power 4 is 256, which is 4 more than a multiple of 4. And 5 to the power 4 is 5 more than a multiple of 4. So, okay, something seems to have gone wrong, but let's not worry about this, and let's move on to 5. And we'll just go through this quickly. 1 to the power 5 is 1. That's 1 more than a multiple of 5. 2 to the power 5, it starts to get a little bit harder to calculate these things. They get bigger. 32, that's 2 more than a multiple of 5. That looks good. 3 to the power 5 is 243, which is 3 more than a multiple of 5. 4 to the power 5 is 1024. That's 4 more than a multiple of 5. So it's starting to look good again. And 5 to the power 5 is 3125, which is 5 more than a multiple of 5. And it turns out that everything works for 5, and it's the case that x to the power 5 is x more than a multiple of 5 for every whole number x. And so we have to think, what is special about 3 and 5, but goes wrong for 4? And the answer is that 3 and 5 are prime numbers, but 4 is not a prime number. And so this isn't Fermat's last theorem, it's Fermat's little theorem that was proven by Fermat, and he did give a complete proof of this, that whenever you have a prime number and you have a whole number x, x to the power p is always x more than a multiple of p. So this is this nice pattern for primes, and this basically only holds for primes. So actually, this is one of the ways that on computers nowadays we test whether a number's prime or not, is by testing whether it's the case that x to the power p is always x more than a multiple of p, and questions like this. So a computer can calculate these things very, very quickly, and this is the main way that computers test whether a number is prime or not. So already this Fermat's little theorem and slight generalizations of it turn out to be things that are used by your computer every day just when you're buying something on Amazon. And just a slightly different way of phrasing Fermat's little theorem that will be useful for things that I want to say later is x to the power p minus 1 is 1 more than a multiple of p if x is not a multiple of p. So x to the power p is x copies of x to the power, it's x copies of x to the power p minus 1. We know that it adds up to x. It turns out that if x is not a multiple of p, then all of these are just 1. So we have x copies of 1, which gives us x more than a multiple of p. But it goes a bit wrong if x is a multiple of p, and then they're all a multiple of p. And we therefore have these nice interactions between multiplying numbers together and prime numbers. So for example, if you were thinking about there being a possible solution to Fermat's last theorem, so if there were numbers x, y, and z, such that x to the power p plus y to the power p was equal to z to the power p, then I know that x to the power p is x more than multiple p, y to the power p is y more than multiple p, z to the power p is z more than multiple of p, and it follows that it must be the case that x plus y minus z is a multiple of p. And so we've already got some non-trivial constraints that have come just from applying Fermat's little theorem to Fermat's last theorem. And this is the core reason why it's easier to think about Fermat's last theorem mathematically when the exponent is a prime number compared to a non-prime number. So we've taken this big problem, the most famous problem in mathematics about whole numbers, and we've usefully reduced it down to a genuinely simpler problem about prime numbers where we can start to use properties of prime numbers. Okay, but that doesn't say anything about what Sophie Germain did, so where does Sophie Germain come into this picture? So at the beginning of the 19th century, a few cases of Fermat's last theorem were known. So I mentioned already that when the exponent was 4, Fermat did solve this case successfully, and building on Fermat's work, Euler had solved the case when the exponent was 3. But essentially, no other exponents were known, and all attempts had been very much in the spirit of trying to fix some small number n and try and work very hard with that specific number n. And one of the amazing things about Sophie Germain's work was that she fearlessly started attacking Fermat's last theorem in complete generality for general exponents p. So in some correspondence to Gauss, she laid out her first line of attack in her dream of how she was going to approach Fermat's last theorem. And it turns out that there were issues with this approach, but I find the approach so beautiful that I wanted to share it nevertheless. So this was Sophie Germain's dream to try and prove Fermat's last theorem in general. So we only need to show it for an exponent p, and she wanted to imagine that there was a counterexample to Fermat's last theorem, so they start off by imagining that x to the power p plus y to the power p is equal to z to the power p. And then the key insight that she had is that you can understand a lot about these sorts of equations if you have useful auxiliary primes. So p is a prime number, but because primes are so involved in arithmetic, you can get a lot of understanding if some small multiple of the prime plus 1 is also a prime number. So imagine that kp plus 1 is also a prime number, and she wanted to show that if kp plus 1 is also a prime number, k times p plus 1 is also a prime number, then k times p plus 1 has to divide one of the numbers x, y, or z. So she wanted to find these auxiliary primes that divided x times y times z, and then she wanted to say that there are infinitely many of these auxiliary primes. So there's infinitely many choices of k such that k times p plus 1 is a prime number. So that means that x times y times z would have to be a multiple of these auxiliary primes for every choice of this auxiliary prime, and so x times y times z would have to be some finite number that had infinitely many prime factors. And it's very difficult for a finite number to have infinitely many prime factors, but there is one finite number which has infinitely many prime factors, which is the number 0. We think of 0 as being a multiple of every prime. But we know that there are trivial solutions to Fermat's last theorem, and this would be showing that the trivial solutions when x times y times z is equal to 0 would be the only solutions. And so she would be showing that there's only the trivial solutions by showing that every solution must have infinitely many prime factors. And so this would then complete the proof of Fermat's last theorem for that prime exponent p. And this is an approach that, in principle, could work for every prime p. And so I think this is just a completely beautiful approach. If it worked, I think this would really be viewed as a sort of fundamental, really, really deep insight, that it's got a lot in common with abstract modern number theory, that often you can't attack one of these famous problems like Fermat's last theorem directly in any way. You have to come up with a very indirect way of getting to the solution. So you can't try and solve x to the p plus y to the p equals z to the p and directly prove that x times y times z must be equal to 0. Here she's going through a very indirect route of finding these auxiliary primes and showing that then x times y times z must have all of these auxiliary primes as a prime factor, and then you, at the very last step, conclude that it must be a trivial solution. So unfortunately, this dream was too optimistic, that this approach doesn't work, and the reason it doesn't work is this first statement, that it's not true in general that if you have one of these auxiliary primes which are some multiple of p plus 1, then that auxiliary prime has to divide the product. So the argument breaks down, but there were very good reasons why Sophie Germain first of all considered this, because this first statement is true if k is a small number. So in particular, Sophie Germain proved the first statement there when k is equal to 2. So if p is a prime and you have this auxiliary prime when 2 times p plus 1 is prime, then 2 times p plus 1 does have to divide x times y times z. So it does have to divide one of these x, y, and z. So this is one of the key results in Sophie Germain's work, and I'd like to sketch the argument behind it because it's not too difficult, and it really gets the core concept of the sorts of ideas that Sophie Germain was coming up with, and it's how she's using these auxiliary primes, which is really Sophie Germain's great insight in Fermat's last theorem. She's very much using the interplay between prime numbers and arithmetic. So if x to the p plus y to the p equals z to the p, then certainly x to the p plus y to the p minus z to the p is equal to 0, which is a multiple of this auxiliary prime 2p plus 1, because 0 is a multiple of all primes. But it turns out that just by checking a few cases, you can see that if all of x to the p, y to the p, and z to the p are 1 away from being a multiple of 2p plus 1, then x to the p plus y to the p minus z to the p would have to be either 1 away from a multiple of 2p plus 1 or 3 away from a multiple of 2p plus 1. But we know that that can't possibly be the case because it's equal to 0 and it's a multiple of 2p plus 1. So saying that in a different way, 1 of x to the p, y to the p, or z to the p is not 1 away from a multiple of 2p plus 1. But if you're 1 away from a multiple of 2p plus 1, you're either 1 above a multiple or 1 below a multiple, and regardless of whether you're 1 above or 1 below, your square is always 1 above a multiple. So another way of saying this is that x to the 2p, y to the 2p, and z to the 2p can't all be 1 more than a multiple of 2p plus 1. Because we've just squared all of x to the p, y to the p, and z to the p. But now we have this auxiliary prime q, which is 2p plus 1. And so x to the 2p is x to the power q minus 1 when q is a prime number. And we've seen already from Fermat's little theorem that x to the q minus 1 is always 1 more than a multiple of q whenever x is not a multiple of q. And we've just said that x to the q minus 1, y to the q minus 1, and z to the q minus 1 can't all be 1 more than a multiple of q. And the only way that this is possible by Fermat's little theorem is that one of x, y, or z has to be a multiple of q. And so this is the fundamental sorts of arguments that Sophie Germain gave, and this is a complete proof of the maybe first step in her big program to try and prove Fermat's last theorem. So she proved various results of this type, and this was really essentially the first general result that anyone had proved on Fermat's last theorem. And she was investigating this much further. She certainly didn't stop at just 2p plus 1 being a prime. She was trying to prove further results with 4p plus 1 being prime. And in particular, she was thinking very much about Fermat's last theorem with exponent 5, and she came up with lots and lots of these sorts of divisibility conditions. And so she showed that any solution to Fermat's last theorem with exponent 5 must have at least 30 decimal digits. It must be really huge numbers involved. You can't possibly have any small solutions to Fermat's last theorem with exponent 5. And so she wrote to Gauss, in translation, you can easily imagine, monsieur, that I must have been able to prove that this equation is only possible for numbers whose size frightens the imagination. But all this is still nothing. It requires the infinite and not just very large. So I really like this. The turns of phrase I find kind of beautiful, but also you can see very much that she was a pure mathematician and she was really focused on trying to prove Fermat's last theorem. And this is an AI rendition of imagination of what Sophie Germain might look like writing to Gauss. Strangely, she's somehow writing upside down in the AI. Okay, so her first approach to Fermat's last theorem didn't work. She had what I find this totally beautiful general strategy for trying to prove Fermat's last theorem, but it broke down because actually when k is a large number, you can't show that kp plus 1 has to divide one of x, y, and z. We don't know how to do this other than by invoking Andrew Wiles's proof of Fermat's last theorem. But it was very much hoped that maybe you could prove Fermat's last theorem first when x, y, and z are not a multiple of p, which was the so-called first case of Fermat's last theorem, and then afterwards there'll be a more technical argument when one of x, y, and z was a multiple of p. And this is somehow related to the fact that if you're using clock arithmetic, then it's difficult to distinguish between the trivial solutions and solutions when one of x, y, and z is a multiple of p. So Sophie Germain had the idea that you should separate out these two cases, and the first case you should consider is when none of x, y, or z is a multiple of p. And she was able to then prove the first case of Fermat's last theorem by building on the sorts of ideas that I explained to you in the slide before, using these auxiliary primes. And so a simple version of what she wrote is when p is a prime such that 2p plus 1 is also prime, so when you have this nice auxiliary prime pattern, then it's the case that the first case of Fermat's last theorem is true. So it's the case that there are no solutions to x to the power p plus y to the power p is equal to z to the power p with one of x, y, or z being a multiple of p, with none of x, y, and z being a multiple of p. So one of them would have to be a multiple of p for any solution. And by using variants of this theorem, she was able to establish the first case of Fermat's last theorem for all primes p less than or equal to 100. So this was sort of testament to the power of her work that she came up with a successful partial general approach. She was proving the first case of Fermat's last theorem, and this actually worked in practice for lots and lots of primes. And very much building on her ideas, just a few years later, Dirichlet and Legendre managed to establish the full case of Fermat's last theorem for exponent 5. She'd done the case when the first case of Fermat's last theorem, because 2 times 5 plus 1 is 11, which is a prime number, so her theorem applies in this case. And then they managed to prove the second case of Fermat's last theorem for exponent 5. But let's go back to Sophie Germain's theorem. So this is a theorem where there's an assumption at the beginning. We need p to be a prime such that 2p plus 1 is also a prime. So nowadays, such primes we call Sophie Germain primes, named after her. But a natural question is, how many primes are there, p, such that 2p plus 1 is a prime number? So this would be a great theorem if for every prime p, 2p plus 1 is a prime number. Unfortunately, that's not the case. And it would be not such a great theorem if actually there was maybe only 3 primes p, such that 2p plus 1 was a prime number, and then it stopped applying to anything. So a very natural question is, okay, so when does Sophie Germain's theorem actually apply? How many primes p are there such that 2p plus 1 is a prime number? How many Sophie Germain primes are there? And this is a wide open problem. We don't know the answer to this. So mathematicians have thought about this for over 100 years, and it's strongly believed that there are infinitely many Sophie Germain primes, but we don't know how to solve this. But it's highly connected to lots of modern number theory research on the distribution of prime numbers. So much of the subsequent work after Sophie Germain's work moved in a slightly different direction, in particular the work of Kummer, who was establishing the groundwork for modern algebraic number theory by trying to develop further techniques to attack Fermat's last theorem. But Sophie Germain's work maintained its relevance, and it was, in the 1980s, one of the stronger results in the direction of Fermat's last theorem before Wyles's work was this result from the 1980s of Adleman, Fouvry, and Heath-Brown that showed for the first time that the first case of Fermat's last theorem is true for infinitely many prime exponents. And they were fundamentally using a generalization of Sophie Germain's original ideas together with results on the distribution of primes, addressing questions which were similar to but weaker than the infinitude of Sophie Germain primes. Okay, but I want to switch gears slightly. So we've been thinking very much about Sophie Germain in the maybe early 1820s and its connections to Fermat's last theorem. But it turns out that primes aren't just useful for pure mathematicians and number theorists like me or like Sophie Germain. They also have applications in the real world. And so I'd like to explain a little bit about the relevance of primes in the real world and then get back to Sophie Germain again. So nowadays, it's absolutely vital that internet communications are secure. So if you want to buy something online, you send over your credit card details, but you really don't want some hacker to be able to extract all the credit card details from you. And so the way that your credit card details are kept secure is that your computer encrypts all of these credit card details so that it isn't just broadcasting the credit card details. And this, it encrypts it in a way that's hopefully very difficult for the hacker to decrypt, but it allows you to have secure communication with whatever website you want to buy things from. And it turns out that many of the most popular cryptographic systems that are used day to day when we're using our phones or our computers involve multiplying whole numbers together. That your credit card number is essentially a whole number, and the way it encrypts it is by doing lots of multiplication steps. And so this is a question about whole numbers being multiplied together. And so you might hope that it can be broken down into a simpler question about prime numbers. And in particular, the question here is how easy or not is it to reverse this process of encrypting and decrypt it. And it turns out that in one of the, if I just fix my attention on one of the most common cryptographic systems in use today, the difficulty of decrypting is essentially the difficulty of turning a whole number into its constituent prime factors. So on the first slide, I wrote 135 is 5 times 3 times 3 times 3. So it's the process of taking 135 and splitting it up as the 5 and the 3 threes. And so, for example, if you take 449,623, the question are what its prime factors, and it's obvious to everyone in the audience, I assume, that this is 521 times 863. But although small numbers like this are maybe easy, or at least very easy for a computer, we believe that this gets very, very difficult when the numbers get very large. So for example, if you take this slightly larger number, this was a famous challenge problem. It was called RSA 896, and there was a $75,000 reward for factoring this number, and nobody succeeded in factoring it. It's possible now that if you threw huge computational resources at it, maybe we could just about factor this number, but it would cost you a lot more than $75,000 to be able to factor it even now. And so it's very easy for computers to encrypt things using numbers like this, but it takes computers a huge, huge length of time to turn them back into their constituent prime factors. And it's easy for computers to use numbers that are much, much bigger than this example. But it's not easy for me to put much bigger numbers on the slides. But it turns out that because this is still a question involving multiplication in prime numbers, you can try and follow Sophie Germain's experience about thinking about auxiliary primes when you add 1 and subtract 1, and what are the prime factors then, because that might give you a different angle in how the arithmetic works, just as we saw in Fermat's little theorem, and just as we saw in Sophie Germain's theorem. And it turns out that if the big number has a prime factor such that when you take 1 away from that prime factor, that resulting number only has small prime factors, then there's a clever way that you can work out all the prime factors of the original number. And so this is a cryptographic attack due to Pollard, and therefore you have to be a little bit careful about what numbers you're using to encrypt your credit card details. If you chose a number badly, it might be very easy for a potential hacker to be able to recover things because they could factor these numbers. And so to get around this, even current generations of cryptographic software like OpenSSL have the option of moving as far away from this as possible. So if you really don't want p-1 to have lots of small prime factors, well, if p is a large prime, then p-1 has to be a multiple of 2. So somehow the furthest thing you could be away from having lots of small prime factors would be being 2 times a prime. And so these are so-called safe primes, primes p, such that when you take away 1 and divide by 2, you get another prime number. But how good or not it is to use safe primes depends on how many safe primes there are. That if there were no safe primes, then your computer would take forever to try and, it would just be searching for ones and you wouldn't be able to buy what you wanted. It'd be even worse if there was a list of just 100 safe primes, because then the potential hacker could also look at this list of 100 safe primes and could try each one out, and then he'd be able to find out which one divides your number. So a natural question that affects internet cryptography, but boils down to just a question in the pure distribution of primes, is how many primes p are there such that p-1 divided by 2 is a prime number? How many safe primes are there? And if you think for a moment, this is exactly the same question that we had before on the infinitude of Sophie Germain primes. If p is a prime number such that p-1 divided by 2 is a prime number, then p-1 over 2 is a Sophie Germain prime. And so we see that Sophie Germain's original work on Fermat's last theorem completely disconnected from anything other than pure mathematical abstract thought, turns out to be relevant even for pretty basic questions on the security of modern day life and internet cryptography. Okay, so we've seen a few examples, both in real-world examples and in Sophie Germain's groundbreaking work on Fermat's last theorem about taking problems involving whole numbers and breaking them down into simpler problems about prime numbers, and then analyzing this a little bit further and running into these questions about the distribution of prime numbers, like the infinitude of safe primes or the infinitude of Sophie Germain primes. And therefore, as number theorists like myself, what we would really like to have is a general theory for trying to understand the distribution of primes and these sorts of patterns about how many Sophie Germain primes are there and how many safe primes are there and other questions that are related to that, and a general set of techniques for answering these sorts of questions. So I'd now like to spend the last few minutes talking about some of the more current research on the distribution of prime numbers. So we've seen some basic problems just about patterns purely to do with prime numbers. How many primes p are there with p minus 1 over 2 prime? How many primes p are there with p minus 1 only having small prime factors? That's how likely would it be that this cryptographic attack happens. But then there's other very closely related questions that are other famous questions in exactly the same spirit. So for example, the twin prime conjecture is another question about patterns to do with primes, which is just asking how close together can prime numbers be. So the twin prime conjecture is the claim that there's infinitely many pairs of primes that differ by exactly 2. So this is asking for primes p such that p plus 2 is a prime number. It's in the same spirit that you have some linear function of a prime itself being prime. And then another famous problem in number theory is Goldbach's conjecture, which is asking whether every even number can be written as the sum of at most 2 prime numbers. So these are all famous problems in number theory. They're all open problems that are unsolved, but they're all the sorts of topics of current research. And although we don't know how to fully answer these questions, we are gradually making progress. So it turns out that all of these sorts of problems are actually very, very similar from a theoretical point of view because they're to do with linear equations in prime numbers. And so I would have guessed that it's quite likely that if one of you, maybe you're a little bit bored in the audience, and so you're thinking about the Sophie Germain problem of the infinitude of Sophie Germain primes, if you manage to work out a way of proving that there's infinitely many Sophie Germain primes, I would have thought that not only would your techniques prove that there's infinitely many Sophie Germain primes and therefore infinitely many safe primes, but I would have thought that a small adaptation of your techniques are quite likely to resolve the twin prime conjecture and also quite likely to resolve Goldbach's conjecture for sufficiently large numbers, for sufficiently large even numbers at least. So I sort of feel that actually the Sophie Germain question, the twin prime question, and Goldbach's question are all different facets of the same coin, and it's quite likely that any technique that worked for one would end up working for all of them, and you'd solve 3 questions. It's 3 for the price of 1. Okay, but we don't know how to solve any of them, so that's all well and good. But I'd like to mention at least a little bit of reasonably recent progress that mathematicians have made. And so in particular, research that I've been involved in as an approximation to the twin prime conjecture, we can't show that there's infinitely many pairs of primes that differ by exactly 2, but we can show that there's infinitely many pairs of primes that differ by at most 246. So 246 is quite a bit bigger than 2, but up until about 10 years ago, we didn't know that there was any number, any finite number that you could put there. It was possible, as far as we knew, that the gap stream primes could just get bigger and bigger and bigger. And so this was the first time that we were able to establish these pairs of primes that come unusually close together. So that doesn't directly address Sophie Germain's problem or the question about p minus 1 over 2 being a prime number. And I don't know how to solve that. But in the same way that I can prove a weak form of the twin prime conjecture, it follows from the same methods that you can prove a weak form of the question of the infinitude of Sophie Germain primes. So rather than, I can show that there exists numbers A1 and A2 such that there's infinitely many primes P such that P minus A1 divided by A2 is a prime number. So if I could take A1 to be 1 and A2 to be 2, then I'd have proven so there's infinitely many Sophie Germain primes. And that would be a different proof of infinitely many primes for which the first case of Fermat's last theorem holds that doesn't use any of Andrew Wiles's technology. We don't know how to do that, but it's a weak version of the question of the infinitude of Sophie Germain primes. And similarly, mathematical techniques are developing, and so you can show more results like clusters of primes coming close together. So the point of this is that even when we're faced with these very famous 100-year-old problems on the distribution of primes, which are often a roadblock to really getting the complete understanding that we would like, nevertheless, modern mathematics is making gradual progress, and we are chipping away at the frontier, and we're gradually making some partial progress, proving weak versions of these questions, like weak versions of the twin prime conjecture, weak versions of the question of the infinitude of Sophie Germain primes. So just to recap everything that we've seen in the lecture so far, and to finish up, the primes are like the atoms of arithmetic, and so when we're faced with a problem involving whole numbers and multiplication, we hope that we can break this problem about whole numbers down into simpler questions about prime numbers. And in the case of Fermat's last theorem, that meant we only needed to prove Fermat's last theorem when the exponent was a prime number. And this was genuinely a simpler version of the problem. And you can further analyze the arithmetic by looking for patterns in prime numbers. So when you have these nice patterns, such that primes P, such that 2P plus 1 is a prime number, we can make further progress because of the link between prime numbers and arithmetic. And so this is exactly what Sophie Germain did. She made great strides in understanding Fermat's last theorem in general when we're in this nice situation of there being these patterns of prime numbers and these auxiliary primes. But quite quickly, when we start asking questions about patterns in prime numbers, we run into famous unsolved problems that have stumped mathematicians for over 100 years. So for example, the infinitude of Sophie Germain primes, but nevertheless, we're slowly making positive progress towards it. Okay, so I think I'll stop here. Thanks a lot for listening. Happy birthday, Sophie.